Well, welcome to the Australian Technology Park. My name is Mohamed and I'm here to give some history and context to how this place came to be. I'm also here to talk about the history and the heritage. History is an easy thing. It's what happened, done by people, we can find that out. But heritage is a much harder concept to get a hold of. So as you're with me, I want you to think about the idea of different but the same. And stay with me on that theme. Different but the same. Different eras, different people, different races and groups, but the same themes are running through. Bear with me. If we had come here when the first Australians were here, before the contact period, we would have found this is an incredibly fertile area. The land around here was green and lush, small ponds, creeks, little rivulets going through here, and naturally the first Australians would come here to hunt and fish. And as they came here, natural roads developed. Those natural roads are places that we call King Street, Cleveland Street. Think about it, you're walking in the footsteps of the first Australians and driving in them. When these people came and they hunted, they also talked and they traded. And therefore think about this, from the beginning, this was a place of trade and transport and communication. And of course it later became Eveleigh. What was Eveleigh? A place of trade and transport and communication. And now it's Australian Technology Park. And what's that? A place of trade and transport and communication. It's different, but kind of the same themes are running through. And if we roll along another 100 years, the fledgling colony of New South Wales is beginning to grow. It's an agricultural society, but it wants to become an industrial society. And with remarkable forethought, what's the only way to do that at that time? Build a railway that will bind the country together and move those products around the place. And of course, you've got to maintain and care for that transport. You've got to keep those trains running. How do you do that? You have to build a railway workshop, and thus Eveleigh was born. They put a man called John Whitton in charge. He, from 1884 to 1887, began to design and build this place. He could have just put up some work bays and some shops and left it at that, but he wasn't that kind of man. He wanted to do what we would now call future-proof the place. And later, Richard will explain how he does that. But think about this. At that time, the little colony of New South Wales out on the edge of the world had created something that was the equal of anything that was made in England and in America. At that point in time, we were leading the world. Something to think about. So let's overwhelm you with some facts. 61,000 square metres. They could service and repair over 1,200 pieces of rolling stock. They built 150 locomotives here. 4,000 to 5,000 people working on copper, brass, metals, from little taps to boilers, making huge locomotives, fixing suspension, doing everything, catering, design, research, building for the future. And what have we got here as well now today? 4,000 to 5,000 people. Doing what? Catering, design, research, development, working on the next future. See what I mean? Different, but the same. Think about these things. And what type of people did we have here working here? Remarkable people came here. Because out of those 4,000 to 5,000 people that worked here over more than 100 years, we have had over 20 different politicians come here. If we start with J.J. Carl, leader of the ALP, Premier of New South Wales. William McKell, leader of the ALP, Premier of New South Wales, Governor General of New South Wales. J.S.T. McGowan came here as a boilermaker, became the representative for Redfern in 1891, later became the Premier of New South Wales. Even more remarkable, one of my favourites, a young lady called Mary Lyons, came here as a nurse. She ended up the president of the New South Wales Nursing Association, and in the end, she got the first industrial award for nurses. Why are these people coming out of here? Because they wanted to work hard and create a better future for everybody. The conditions in here conditioned them to want to improve things. And what did they talk about here? They talked about here the 8-hour day, 5-day week, workers' rights, equality for Aborigines in the 1900s. And by the 1950s, they were actually discussing things such as Aboriginal land rights here and equal pay for Aboriginal peoples. Such is the calibre of people that worked here. And think, What's the calibre of the people working here? What new ideas will come out here? What new thoughts will come from this place as well? So yes, it's different eras, different people, but it's the same themes running through. That's same but different history and heritage.
Well, my name is Richard Butcher there. I worked here in the 1957 to 1962 era. By a lot of hard study, I was then elevated to the welding engineer's position for New South Wales Government Railways, but it was interesting working in this workshop. Where we stand at the moment in Bay 1 is a very old site. The first 4 bays were opened in 1887, so they're oldest on site. They're the largest too. They're, the first 4 bays are 60 feet wide, and then they diminish down to up to Bay 15, which goes down to 50 feet of width there. But the work was very hard. There was no running cold water. You stood over a forge fire all day. The heat was enormous. We used to do a lot of forge fire welding. In this workshop particularly there, we have a machine very nearby called the Davy Press. The Davy Press used to have 2 steam locomotive boilers to service, raise steam, to drive the huge 1,500 tonne Davy Press there. When we cut off billets of steel, and maybe we'll pan in that a little while later there, we'll see some of the ingots. In this particular section, we have an overhead crane because we're limited to 5 tonnes weight of what billet or ingot of steel we can lift up. Now, it would take maybe up to 4 to 5 hours to heat this billet of steel up there to bring it out to forging temperature. The forger was a highly paid man because that piece of steel, maybe in today's value, maybe $5,000 or $6,000, that ingot of steel. If the furnaceman or the forger overheat it, you've destroyed the piece of steel, so straight away it's been ruined there. You had to have a team of about 6 people. There was an overhead crane in this section, and a chap by the name of Ted Bocott, he used to be the driver of the crane there in the 1950s, 1960 era. The forgers were Bill Lawrence and Harry Lawrence. They were quite characters to watch on the floor. It was like running a circus show there, and you had to get a giggle out of it there. But where the forger spoke, everyone jumped to attention. If the job was hot, he'd say, righto, off your backsides, let's get out of the job. So then you would have to affix a thing called a porter bar to manipulate the piece of steel that you're going to put under the press. The forging range may be 1300 degrees centigrade, which is yellow-white temperature there. Mild steel, if you're working with mild steel, melts about 1400 degrees centigrade and just above that temperature line. But you may have been forging different types of steel. This old building is held up by what we call cast iron columns and beams, which are very near at the moment. The roof structure itself is wrought iron, is held up by wrought iron on this huge space here at the Eveleigh Railway Workshops there. The Davy Press is just to the rear of us there, but to use a Davy Press you have to have heavy die blocks. And we can see sitting here there are numerous die blocks. They're very costly, these die blocks, because they have special steels in them. Molybdenum, chromium and nickel, because when you forge a piece of material, it has to be harder than what you're forging as far as that goes. So there are numerous die blocks here. I dare say a pair of die blocks, you're probably looking in the order these days of $10,000 for a set of die blocks there. They do fit into the press itself there. Well, now we've just moved away from the die blocks to all the tools that we used to use underneath the Davy Press. And although they look all weird and wonderful and colourful in their shape type of thing, each served a purpose. We can see laying on the ground, if it's possible to the camera follow, there's a hook. It's just a simple, very small draw hook off a locomotive there, a typical thing that was forged at this machine. But all the tools were very, very heavy. And I know I was only about a 20-year-old apprentice when I had to work here for about 6 weeks in the late 1950s. And just to pick one of these tools up, the weight was enormous there. There's spanners laying around the workshop, I think weigh over 20 kilograms just for one spanner. So, you know, it was a lot of brawn and hard type of work. The forgers generally were pretty big fellows, pretty strong type of people there to do the work that they had to do. As I said earlier, where we're standing here too, we're very near the table and chairs where the men used to sit down and wait, and the crane man till the job was hot. The furnaceman would yell out, now we're up to temperature there, and then the crane driver would remove the item from the furnace and then go underneath the die blocks themselves at the press. But the work was very, very heavy and very, very hot, but we survived it. Okay, well, we're standing near the Davy Press itself there, and on the ground, in the foreground, we see a few different items. If we look just at the base of the machine, we see some funny twisted shaped pieces of steel. They're equalising beams off mainline diesel locomotives. If you could kind of visualise, where that curls around here, there's a wheel in there. Those two go together. There's a wheel in there and another wheel there. The finished items are probably very, very, very valuable. Maybe $12,000 each. But you look at a piece of steel and it just looks a humble piece of material, but in real value, it is very, very valuable. Also in the area, we have some of the porter bars which we use for manipulating our materials underneath the Davy press there. I might have mentioned earlier, you heat the material up and you've got a forging range. All materials have a forging range, and if you go beneath the forging range, you can start to destroy the grain structure of the material. So there's a lot to it, a lot to do with metallurgy. And I did mention earlier this building, maybe we could do that later. We could show the twin cast iron columns which hold the roof up. They're made of cast iron, basically 4.5% carbon content. The major framework in the roof is wrought iron, which is nearly pure iron, might be only 0.03% carbon within the material there. The die blocks still have a bit of carbon in them, but we'll have all these fancy materials like maybe cobalt or chromium or nickel that will stand up with the heat, and also a lot of heat. And remember, the press squeezes, so if you had rubber steel there, it'd be completely distorted. So we want something to retain its shape even under heat and extreme pressure there. I've done some drawings over a period of time since I've been helping out as a tour guide here with the Australia Technology Park. But we see here basically the format of a steam locomotive. What it simply means, 32 was a 32 class locomotive, and they built a fair few here at Eveleigh. 29 happens to be the 29th one built. But being a blacksmith and forge shop, where all these little black dots are indicate what blacksmiths used to forge up there. The draw gear, the hooks and the chains, things for the grate of a locomotive there, the eccentric arms, the connecting rods which are in the lower drawing type of thing. And we did use the Davy press for a lot of this work. There were also steam hammers in this workshop when I worked here. Also at the other end of this workshop we have a heavier forging press, and that came from the very first workshop here, which went back to the Cleveland paddocks. There, in the early days, of course, Redfern Station was called Eveleigh Railway Station there, but Eveleigh, as was stated before, was a big employer. I have read at one stage it got well over 7,000 people happened to work here, and it was a big organisation there, so close to the city of Sydney too. So yeah, so I just did some of these sketches up of maybe with a little dots indicate what was forged, and yes, we had to keep 1,200 locomotives steaming on the rails. We did a little bit of carriage work here, although carriage works is on the opposite side of the tracks here at Eveleigh, but of course also brand new locomotives were constructed on the site there. Yeah, well, we're still in there Bay 1 where the Davy press is, but the blacksmith shops traditionally you couldn't work on tarred surfaces because you're always forging hot material. If you lay the hot forging on the tarred surface, it's going to catch on fire. You certainly couldn't have wood because you'd burn the building down. Cement, if you lay something hot on cement, it literally explodes. It just fragments and blows up. So the floors in these workshops were basically dirt floors there, very fundamental floors. And in the background we have a furnace. Years later, furnaces were installed for heating up our larger piece of material. Most of the furnaces were oil fired, but with oil firing, oil is carbonaceous and it cooks more oil in. Oil is carbon, and the carbon content is very critical in our materials that we happen to forge up these days. So it was good in one way and bad in another way there. Natural gas would have been better, but in the area the workshops did open in 1887 and they closed literally in 1988. But if you could have used natural gas, it would have been more, say, inert to heat a piece of steel up there, but the carbon would impregnate additional carbon in the material. We've now moved into Bay 2, which is principally there for the blacksmithing trade, but of course blacksmiths forge materials up there. We had, in one section there, we had the toolsmiths where they forged specialised tools, or lathe tools, or milling machine tools, all this type of thing there. And we had more of the traditional repair work going on here. I think there's only about 4 steam hammers in here today, but when I worked here there must have been maybe 12 steam hammers. A steam hammer is a very, very fast machine. Very dangerous. It takes 2 years to train a young person or an older person how to operate a steam hammer, because the action is the piston kind of goes up and down all the time, and they're very, very quick. And if you blink, maybe you lost your life or something like that. They're very dangerous machines. I only ever seen one person hurt when I worked here. He ended up 3 weeks in Missington Road Hospital there, tongs come off the job, and we'll pan in a little while later. We'll have a look at some of the tongs that we used to manipulate our work with there. There was around 56 men worked here, predominantly blacksmiths, and there was also the blacksmith strikers there. Being a steam workshop, we were just having a look at the steam hammer. When the shop was activated in the morning, 4 big boilers on the outside there. If we kind of look skyward, we see a pipe up here which has got an expansion joint in it. So when the chap would open up the main control valves in the morning, the whole workshop would kind of become alive. The air also in here was smoky. There was the sunlight used to filter through, and in the sunlight there was little sparkling, glistening pieces of coke and coal floating around. I'm still alive, so it never hurt me, but that was the way, and the aroma was beautiful from the burning coal. So it was a very interesting place to work in there. So okay, we're still inside the blacksmith shop, and we see anvils, and anvils are an essential item to use in the blacksmith shop. Ones here are very heavy, 500 and 600 weight. 100 weight's 112 pounds weight, so I don't know what that is in kilos, but it'd be very expensive to buy one today. They're getting very, very rare. And we also see the forge fire, which has a chimney which goes through to the roof on the outside. The basic fuel we use was coke. We'd light the fire up of a morning using a bit of kindling wood, or maybe a bit of kerosene with a few pieces of timber covered with kerosene to light the fire up there. Then we used to bring the fire up to temperature, and then we would go on to coke. Because the coke, unlike, you can't use coal, because again coal has carbon in it. So you're going to cook carbon into the matrix or into the base material that you're working with. Coke gives a good fine burn. It's very, very old material, coke, and it gives a very, very good burn. The coke bin, you can see, is a little square box on this side of the fire. That's where the coke used to be. And the best size was a small, we used to call it peanut size for doing our heating. A lot of forge fire welding. There's fires just here. I used to do a lot of forging here and fire welding. Fire welding is nearly a lost art now, and I reflect an older age, and I just can't believe what we used to do. You had tools to pat the fire down. It's slack coal, which is very fine coal, and you'd build up more or less into castles, and you'd pat it down, because your fire, no matter what you was doing, just coincidental where this steam hammer is sitting there, there's a thing called a ram hanging there. And the ram is what we used to use for shortening materials. A connecting rod and locomotive, the big rods which go around the outside. The fitting machine shop from down Bay 8 or 9 will come up and say we have to have a rod shortened 1/8 or 3/8 of an inch like it. We'd build a special small forge fire and heat the material up, put trammel marks on it for the precise size that we want. Then that ram hanging down there, or the rope, you get 3 or 4 men to pull the ram back, weighs about 50 or 60 kilogram, and bang and hit the job. You had to be pretty accurate because someone could get hurt. That was part of our work, lengthening or shortening of connecting rods or coupling rods on locomotives, and also other items that were on steam locomotives there. We see a machine here. This is a bit unusual. I know these are very dangerous machines. This is called a phrasing wheel. It's got little teeth on it. So when we do something in a forge fire, we may drop forge something, you get a fin. That's the overburden material you don't want. You forge it between the dies and you get what you call this overburden. We'd heat it up, we'd run out here and put it under this and grind it off. The only catch was the little pieces of metal that you ground off, when they hit the body, they would kind of burn holes in you. So when you finish grinding, you go back and have blood pouring down your arms. That was very, very typical. On the other end of this is the grinding wheel. A decent sized one too. It's about 6 inch diameter, 2 inches wide. So, but the railways would manufacture a lot of their own equipment. This machine could have been one of hundreds made at the workshops. They used to manufacture their own vices, their own small lathes, sometimes milling machines, all different types of apparatus there. They had the capacity for doing anything. The railways was a big organisation. In the 1955 era, they employed 56,000 men and women, and they had every tradesman from angle iron smiths, blacksmiths, forgers, boiler makers. They had the boiler makers helpers, the blacksmiths, strikers, fitter machinists, tool makers, tool smiths that just went on, painters and car and wagon builders. They had the works. So it's a big institution there, the old railways. You may happen to notice there that I'm wearing a paper hat. I didn't really wear a paper hat when I worked here, but a lot of the workers did, because one, the newspapers come out every day, and if you had a small head, you'd use the Daily Mirror or the Telegraph or the Sydney Truth, or if you had a big swell head, you'd use the Sydney Morning Herald, because they were larger format newspapers there. One of the troubles is they would keep your hair clean, but while you're working, you'd always end up with someone with a little bit of waste, that's old cloth, with a bit of kerosene on it, and they just put it on the top of your hat, and then when you wasn't watching, they'd light it up. You'd be working in the middle of doing something, next minute you're on fire. The other thing is we've just been looking at forge fires, and because it's very awkward to go into a barber and get your hair cut there, someone would, Big Don Fromola, big tall, strong type of chap used to work here, for 2 and 6pence, 25 cents, he would cut your hair. So there was a little around the back of the forge fire, there was a little tent city made there, and you go around the back, you sit on the kerosene drum, the old tin ones, and you have a pair of hands. There was no electric, there was no electricity at all, because it was too dangerous. There was maybe 32 volt, which is a safety type of item there, but normally 240 volt didn't exist. Same as the work was hot, but there was no cold refrigerated water. It was 100 degrees Fahrenheit outside, it was 200 degrees Fahrenheit in the workshop type of thing. Pretty tough going there. I think at this point there might be an idea that we maybe go out and see where we got our steam from in the boiler room just outside the blacksmith shop there. Outside now are bays 1 and 2, the old 1887 blacksmith shops there, and we may see behind us 4 locomotive boilers. The blacksmith shop was principally a steam operated workshop, and most of the steam hammers and all the steam hammers really work by steam, which govern the whole operation of the workshop there. A little bit of air equipment here and there, but mainly it was a steam operated workshop. So behind us we see 4 C36 class boilers. Normally the 36 class used to operate at a higher working pressure, 200 pound per square inch, but these are reduced to 100 psi. When I worked here in the late 50s, they were fired by coal, and later they were converted over to burn, I think it was oil. They were run on oil, and then you have a blower to intensify the fire and get the fire going there. So yeah, that's the boiler house, and the boilers were replaced over a period of years because in 1887 when the place opened up, they had much smaller locomotives and much smaller boilers to run the operation of the workshop there. So we wind down now there. We've had a tour of the blacksmith shop, the heritage of it. It's very, very old. Certainly I've been lucky enough to get around the world. I've been to America, I've been to England, and the Eveleigh workshops there are absolutely outstanding there. They just have so much to offer there, and it was a pleasure and a treat working here. And I also thank the Australian Technology Park for recognising that it was such an important, valuable Victorian heritage site here in New South Wales.
Well, we've just been to the boilers and seen the boilers that produce steam for the use throughout the blacksmiths area here at the Australian Technology Park. But this particular little powerhouse that we're in speaks or shows an innovative approach to getting power. Any industrial enterprise needs some sort of power, and in the early part of the 19th century the main source of power was through burning coal to produce steam, and then to use the steam to provide mechanical energy to machinery and equipment. And this was commonly done using line shafts and belts, and I'm sure people have seen photographs of old workshops with hundreds of belts bringing the power down from the roof line to the actual workshops themselves. So in the early 19th century, the main source of power here and in other places was that of steam. However, gas came online, but in the early stages, gas engines were not produced, and therefore there was no means of using gas for a power supply other than for heaters. Another source of power was pneumatic power, whereby compressed air was produced using mechanical machines, and that compressed air was stored and then reticulated throughout factories. And pneumatics, as the use of air is called, was used here at Eveleigh, and it provided another source of power. But one of the big problems was to be able to have a single source of energy and to then reticulate that through the factory for use by the various machines. In the early 19th century, a chap called William Armstrong developed a system whereby he could raise the pressure of water and then reticulate the high pressure water throughout an industry with a view to driving machinery from it. So here at the Australian Technology Park at Eveleigh, we've got a small powerhouse devoted to supplying high pressure water through various areas of this enterprise. As an aside to the setting up of high pressure water, we need to recognise that Sydney City had a high pressure water supply system operated by the Sydney Hydraulic Power Company, and they reticulated water throughout the city on about 80 kilometres of pipes, and those pipes, that high pressure water was used to power lifts and cranes and wall presses in various areas within the city. So we might just take a tour through the production of high pressure water so people can understand how it was carried out in the mid-19th century. This system was actually opened in 1886, which was a year before the remainder of the blacksmith shops were fitted out and made operable. The principle was to take a steam engine, to let it drive a pump, to pump water into what is an innovative device called an accumulator, and the accumulator was the device that raised the pressure of the water, and then the water was reticulated throughout the factory to drive various types of machinery. So if we have a look at the process here in the pump house, on my left at the wall you can see two major pipes. The one on the left is the supply steam pipe from the steam boilers next door that we just saw, and you can notice there on the wall there's a steam pressure gauge to give us some idea as to what the incoming pressure was. And the steam engine is here in front of me, and the supply steam came from the wall under the floor to the cylinders of the steam engine, of which I'm standing beside one. The other pipe on the wall was for the exhaust steam, such that once the work of the steam engine had been done, the waste steam was exhausted to the air. The steam entered the cylinder here in front of me, and that pushed the piston backwards, and at the other end of the machine there are pumps that took supply water, and the pumps pumped the supply water out to the accumulators, which are outside this building. This is a twin cylinder steam pump, or steam engine and pump system, and you can see the large flywheel at the back there, which maintained the motion of the engine whilst it was running. At the pump end here we've got a cylinder with a piston inside it, and the piston has the same stroke as the steam piston, but it takes water and forces the water through these large pipes, the one there at the back of the building. The older Fielding pump was replaced by the Haythorn pump here on my left. If you look to the front, you can see the electric motor that drove the Haythorn pump. That electric motor is some 75 horsepower. It provided rotational motion which came through these gears that are covered up by this shield, and the rotary motion was then transmitted into the pistons of the pump that are here on my left. The Fielding steam engine is a twin cylinder steam engine, and when it was replaced with the Haythorn pump here on my left, it was replaced with a 3-cylinder pump system, but running at slightly higher speeds. This system typically supplied high pressure water at something like 600 pounds per square inch, and if we compare that with the pressure in our tyres of our motor car, which are about 30 pounds per square inch, you can see that there's quite a considerable gain in pressure, and therefore a gain in energy that is stored in the system. The Fielding pump and the Haythorn pump both did the same sort of work. The 1886 Fielding pump was, as I said before, replaced in 1914 with the Haythorn pump, but thankfully this engine was stored, was held for supplementary operation in case of breakdown of the Haythorn. It was here as a backup piece of equipment. The Haythorn pump worked right from 1914 through to the closure of the works in 1988. The question that needs to be answered now is, how did they raise the pressure of the water when these pumps, if they just simply took water and fed it through the pump system and out the other side, it's not much different to a dispenser, a bathroom dispenser for liquid soap, because if you just push the plunger down, the soap just simply escapes from the valves that are in it. That's the way that is done is by virtue of the accumulators, which in this particular powerhouse are located outside. Within the little pump house, we've got a situation where water is fed into the pumps, and the pumps pump the water through to the devices behind me called accumulators. We've got two accumulators here, and they raise the water supply pressure through to 600 pounds per square inch. And then that water, that high pressure water, is reticulated to machinery in the factory. So how does an accumulator work? Well, you might like to think of this as a large can with a piston at the bottom, and the feed from the pumps comes into the bottom of the accumulator into a cylinder that has the piston sitting in it. Now the piston is rather small. Here at Eveleigh, the piston size is around about 10 inches diameter, and in the can or the canister or the drums that you can see here, there are heavy weights, and the water that is being pumped into the system by the pumps has to work against those weights. In actual fact, the total weight here on each of these accumulators is 80 tonnes. So we've got 80 tonnes of mass sitting on a 10-inch piston. So the pumps are continually supplying water into this system. So the pumps have to create enough energy to pump water into the accumulators, and as the accumulators operate, they will rise and fall. So as the pumps operate and there's no output to the factory, then the accumulators the pumps will actually force the accumulators to rise. And you can see that the two accumulators here have guide rails, and you need to also remove the stabilising beams underneath the accumulators, because they're not part of the original system. They're there simply to maintain these accumulators in a safe position. So the pumps pump the water into the accumulator piston. The accumulator itself rises, and this particular pair will rise about 20 feet into the air. And then when the factory starts to use that high pressure water, for example the Allen strikers in the blacksmith shop, which used high pressure water, when an operator started to use that, then obviously that person was using water from the system. So now when the accumulators get pumped up to the top of their stroke, the pumps actually stop. And then when water power is used from the system, the accumulator will drop, and gradually it'll drop down and down and down, and if there's enough time spent, enough water used from the system, then the accumulator will actually get down to the bottom of its stroke, whereupon the pumps will start again, and they will start to pump the accumulator back up to its maximum. So as water is pumped into it, the accumulators rise. As water is used from it, the accumulators fall, and the pumps are continually coming on and off to maintain sufficient storage and sufficient pressure in the system. The interesting thing is that the hydraulic power system provided a source of energy that was quite different to that of high pressure steam and gas, but gradually, as gas engines developed and then petroleum was discovered and petroleum engines were developed, and by the turn into the 20th century, we have electricity taking over most of the applications of mechanical power, a lot of the applications of mechanical power. And so gradually the use of high pressure water was discarded, and machinery and equipment was particularly driven by electrical machines from the early 20th century onward.